and to calculate the thermal energy this radiator can transmit to the environment, you need to consider the coolant flow. Yeah, in this case, just as an example, 1 kilogram per second, as well as the airflow. As I told you, 0.4 kilogram per second, and a mean temperature gradient towards the environment of 60 Kelvin. Which power would you calculate this radiator can transmit to the environment? So it's about three things. It's about the coolant flow, it's about the airflow through the radiator, and then it's about the temperature difference between the coolant and the mean temperature difference between the coolant and the environment. And for the given numbers, 1 kilogram per second and 0.4 kilogram per second for the airflow, which thermal power would you calculate this radiator can transmit to the environment?
Would it be 24 kilowatts around there?
Exactly. Can you maybe explain? How did you calculate?
Sure thing. So you can go on your x-axis to 1 kilogram per second for the coolant flow, and then onto the 0.4 kilograms per second airflow line. Then go across onto your y-axis for your specific heat flow, get around 400 watts per Kelvin, and then you set a temperature difference of 60 Kelvin. So you just multiply 400 by 60.
Excellent. That's correct. So under these circumstances, the radiator could transfer 24 kilowatts to the environment. And next question to you now is, so if this one is not sufficient, if you need more heat transfer to the environment to keep the engine temperature stable, so what would you do? What would you do? Would you increase the coolant flow or the airflow, and how can you do this?
We'll increase the airflow, as we can see from the graph that if we increase the flow of the coolant, it doesn't change the heat transfer doesn't change much. But
Exactly.
as the airflow increases, the heat transfer is quite more. So we can do it by placing some fans or maybe increasing the speed of the vehicle, I guess.
Yeah, very good, very good. Thank you very much. So as you can see, if we increase the coolant flow, which could be done by the coolant pump, we cannot achieve a way better heat transfer. But if we increase, as you just mentioned, thank you very much, the airflow, then we can for sure raise the power of the radiator in this case. Okay, great. Then in the next picture, we can see the structure of radiators. So as I just mentioned, one of the major advantages of the liquid cooling is that the radiating surface may be about 50 times higher than the projected surface. And how can this be achieved? Again, shown in this picture here, the radiator uses a special geometry to increase the surface which is covered, which is touched by the airflow. There you can see on this picture, there are lots of many small fins established in such a radiator, and therefore the surface which is covered, which is touched by the airflow, is approximately 50 times higher than the projected surface. So this would be the projected surface, but if you then use many fins like shown on this detailed picture here, then you can dramatically increase. So this is the way the air goes, and the red arrow shows the way of the coolant. Yeah? The coolant flows in on the left side and then transfer the heat to this fins and then again to the air. And this helps to dramatically, as I said, increase the radiating surface of the radiator. But nowadays, actually, it's not only about just one radiator in front of the vehicle, but actually many of them. So as we already talked about, we have different fluid circuits applied in state-of-the-art vehicles. For example, we might have a radiator for the battery. We might have the condenser of the AC system. We might have a radiator to cool the power electronics of a hybrid electric vehicle. We have the radiator for the actual coolant of the engine and so on. So many different radiators in sequence, one after the other. And at the end, there are then the fans to support the airflow in case the airflow by just driving the car is not sufficient. All these different fluid circuits, they need to deal with different temperatures. Yeah, for example, the battery radiator is maybe at a very different temperature than the coolant radiator. And question to you now is, so in which sequence should you place these radiators in terms of the temperature? So there are some fluid circuits which are cooler and some are hotter. And in which sequence would you place it?
Lo único que te puedo decir es que está que te cagas.
Sorry, sir, can you repeat the question?
Yeah, sure. So as I said, we have different radiators for different fluids, and these different fluids, they need different temperatures, right? So for example, the engine oil needs to be cooled down to another temperature than the coolant, or maybe the gearbox oil, and so on. The question is, which sequence would you choose when you need to place the radiators in front of the vehicle? Which sequence should you go for?
Okay, so I think the engine oil radiator will be the first, then followed by the coolant and then the gearbox.
And how could you explain this?
Just from experience, I can't really explain it.
Mm-hmm. Okay. When it comes to the temperatures, how would you judge on the temperatures of these fluid circuits? So the engine oil, is it hotter or cooler than the coolant?
Oh, the engine oil will be hotter than the coolant.
But anyway, you would place it in front of the coolant, right?
Yes.
But what happens then? So if the air, if the coolant, if the air first passes the hot radiator and then going to the radiator of the cooler fluid, what would happen then?
I think the coolant will increase in temperature.
Yeah, exactly. But this is exactly what you don't want to have, right?
We will keep it in the increasing trend. For example, first the coldest one, then
Exactly.
the hotter one, then the hotter one, then the hotter one.
Yeah, exactly. So this is the right answer. So regarding the sequence, yeah, you first need to place the coolest fluid in the airflow, and then passing by hotter and hotter radiators, right? So at the very beginning, yeah, there must be the coolest fluid, and then step by step you increase the temperature, because if you do in another way, then you would just heat the following radiators with the hot air of the first radiators. So always from cold to hot in direction of the airflow. So this is very important. And another thing, which is also mentioned here on this slide, nowadays there are some fluids like the engine oil, which no more have their own radiator in front of the vehicle, but which transfer their heat to another coolant circuit by a heat exchanger. So as shown on this picture here, most likely the engine oil has no more own radiator in front, but uses a heat exchanger to first pass on its heat to the coolant, and the coolant is then cooled by the radiator in front of the vehicle. Okay. Yeah, now let's check different.
So I do have a question.
Sorry for interrupting the session. Like, can we know why the session is not being recorded?
Oh, I think it's recorded. I will
No,
upload
it's not.
that, okay? It's not? Okay. Sorry for that. Let me check. Quickly check. Okay. Just 1 second. I thought I started it. Okay, can you maybe a little bit support me? Where can I start the record?
So it will be easier if you were using your school account, but you're using your personal account. So I think that's where I can record it.
Mm-hmm.
Because you're right there in the thing which we need to record, but that's how all other professors does. But I don't know why you are not able to do it.
Mm-hmm. There should be kind of button here, right?
Yeah, your button is being disabled.
Okay. Then maybe it's restricted by our IT department. This could be the case.
Okay.
So sorry for that, but yeah, then you need to carefully listen, which is also an option, right? Okay. But maybe one more remark to this, yeah. As promised yesterday. So first of all, I will provide a beautified version of our sample calculation. So don't worry about that. Yeah, you will be very well aware of the calculations. And in addition to that, I will also provide a questionnaire via the Blackboard with all relevant questions for the exam. So don't worry, you will be really well aware of what is relevant. And I will also arrange another lecture in the beginning of next year to again repeat the most important topics for the exam. So really don't worry. As I said, you will be well aware of what is of importance and how to best prepare for it, okay?
Awesome. Thanks, sir.
Yeah, very good. On slide 91, you can now see different positions for the radiators, yeah. By checking the numbers, yeah, you can easily identify where these positions are in the vehicle. Number one is let's say the most common one. Yeah. So most common is to place the radiators with a comparatively large area with direct utilization of the wind in the front of the vehicle. So this one ensures the best cooling, and this one also ensures short tube lengths for front engines. So this is especially of importance for the charge air. You can imagine if you have a rear engine and you need to distribute the charge air first to the front and then to the back. Again to the engine, then you might have a lot of pressure drop and so on. So this is not the right approach, but it's the right approach for the front engines. Yeah. Then also state of the art to place additional radiators, especially for powerful front engines, in the wheel housings of the front, to achieve a better or let's say an additional cooling there. Then, especially for race cars, it's very common to place the coolers, the radiators, on the position marked with a 3 here, because then the flow of the air is very smooth, and you have little losses caused by the air track. And last not least, for rear engine, again to keep the tube lengths short, the radiators might be also placed in the back of the vehicle. Okay, when idling, when there is no real airflow by the vehicle speed itself, there might be some critical situations because of the venting of the radiators, right? So it's not only about getting the air in front of the radiators to let the air flow in the radiators. It's also about the venting again. So after passing through the radiators, the air must again leave them accordingly. And when idling, there might be the risk of circulating air. So as described here, marked with the A, and additional backflows as shown by the figures B and C. So there might be a risk of heat accumulation, which must be avoided by a proper ventilation of the coolant air again. And this one can be achieved by using a fan. So as shown some slides ago, in the very end of the radiator package, there is a fan to suck the air from the radiators and release it again to the environment. And this fan is only effective until a certain velocity. So until reaching, let's say, 80 or maybe 90 kilometers per hour, this fan might achieve an additional airflow. But when surpassing this velocity, the airflow provided by the actual wind is even higher than the required air mass flow. And by then activating the fan, you cannot achieve any more. Actually, it's the other way around. When you are higher than this speed, as I said, 80 or 90 kilometers per hour, then the wind would actually propulse the fan and not vice versa. So this one helps for low speeds, but at higher speeds, this does not help anymore. Okay, some minutes ago I was just asking, which one is better for the particular case shown in the performance map of the radiator to increase the coolant flow or the airflow, and the answer was for the particular case, that the increase of the coolant of the airflow is much more effective. And then the question was how to achieve that. And as already described, the need of air mass flow is highly depending on the actual operating point. Yeah. So when it's very, very cold, when the vehicle is operating at a little load, then you might not need a very big airflow. Maybe you don't need even some airflow. And then it's about blocking the airflow, because as you can imagine, if the air flows through the vehicle, so starting at the front of the vehicle, passing by the radiators, passing by the engine, and leaving again to the underfloor, the air drag is very high. And this one must be avoided. And for such situations, when there is no need of the airflow, you can even close the radiators completely. Yeah, you can completely shut down then the airflow, and this helps again to decrease the air drag, and then also helps to warm up the coolant and the engine much quicker. There are different options. Yeah, maybe you know about the Lamborghini Murcielago, which has even got some radiators, let's say, which can be activated or deactivated again if not needed. So you can see on this picture here, the radiator is open. Yeah, this one is applied when there is a need for cooling, for applying the airflow to the radiator. And if it's not needed, so as shown in the picture here on the right, it can be completely closed again. And then you have, as I said, two advantages. You have a reduced air drag, and also the engine becomes much quicker warm. A very important or very interesting, let's say, concept is shown here. The BMW i8 Roadster has got a very special design of the air mass flow path. Yeah, the coolant air enters in the front of the vehicle through the BMW kidney, going through the radiators, and then not leaving the vehicle again by the underfloor, which is state of the art. Yeah, as can be seen here. But the hot air is then released again through an opening, through a gap in the hood. And can you imagine what's the reason for that? So standard, as shown here, is that the air flows into the vehicle in the front and then leaves again through the underfloor. And for the i8, it's different. Yeah, it again flows into the front but leaves through a opening in the hood. So what could be the reason for that? Can you imagine?
Could it be for increased grip for the tires?
Exactly. This is the reason. Because
to create more downforce and
exactly. Exactly.
And so, reduce the drag.
Exactly. So maybe not so much reducing the drag, but if the air flows through the engine compartment and then leaves again on the underfloor, you might even reduce the downforce by doing so. If you steer the air flow in another way and release it on the top of the hood, then you might even increase the downforce, which is especially of importance for a sports car. Okay. Yeah. The very bad story about the cooling system is that you even need to spend power on getting rid of waste heat, right? So this is actually a very bad thing. So on the one hand, you lose energy, you create waste heat, and on the other hand, you even need to spend more power to get rid of it. And this one can be seen on the diagram on this slide here. So we have actually three main contributors to the power demand of the cooling system. So the first one is the increased air drag caused by the cooling system. So this one rises very much, as you can see, with the velocity. So when traveling with 250 kilometers per hour, you spend approximately 10 kilowatts just because of the increased air drag of the cooling system. Then you need to consider additional power, especially at low speeds, as just explained, for the fan. So also you also need to consider maybe more than 1,000 watts to power the fan, and then you need to spend some power on the coolant pump, and this leads to an overall demand of way more than 10 kilowatts when, as I said, running on high speeds just to get rid of the waste heat. And this is, as I said, a bad story because you spend energy in order to get rid of energy. Okay. Yeah, on the next slide, you can then see the different types of liquid cooling. So in the very beginning, so several decades, more than 100 years ago, there was the evaporative cooling applied. Means this one was not kind of sophisticated coolant circuit with a pump and so on, but actually the engine block, the cylinder head, was just filled with some liquid with water, which then evaporated during operation. And this one is actually very, very simple, as the evaporative temperature of the water is constant for constant pressure of 1 bar of the environment. You can even achieve a very stable coolant temperature. But the bad thing is you always need to refill the coolant tank, because the vapor just flows out, and then you may even need more coolant than petrol to cover a certain distance. So this one is definitely not what customer is requiring for, and therefore nowadays for sure we have a closed coolant circuit. So in the meantime, also several decades ago, there was a thermosiphon cooling applied without any pump, but the mass flow of the coolant was just achieved by difference in density. As you know, when the coolant is heated up, the density goes down, and therefore the coolant went up, let's say, in the cycle, cools down again, density becomes higher, and this is actually the driving force of such a circuit. But for sure, the capability of such a propulsion, let's say, of the coolant is very little, and this is why nowadays we have the forced circulation cooling. Means for sure also a closed circuit, but the propulsion is covered by a coolant pump, which sucks the coolant from the radiator, pumps it through the engine, and then meeting a valve, a so-called thermostat, which either passes on the coolant directly again to the pump via bypass. When the engine is still cold, you don't want to send the cold coolant again to the radiator, but you don't need any cooling and send it back to the coolant pump directly to ensure a quick warm-up. And when the required temperature is achieved, the valve opens and sends the hot coolant then to the radiator to cool down. Yeah, which requirements are important for coolants? Yeah, this one can be seen on slide 101. For sure, the coolant itself must have a sufficient specific heat capacity as well as heat transfer properties. For sure, it must be frost-proof, no boiling, high thermal stability, protection against corrosion, very important for the engine, low electrical conductivity, little tendency to oxidize. It must be compatible from a thermatological point of view, no toxicity, compatibility with polymers, no rubber swelling, and paints as well. So when the coolant gets in touch with different material, for example rubber, but also for example the paint of the vehicle, it must not cause any damage, and for sure low cost and lifetime filling is required. And yeah, in order to cover all these requirements, nowadays the coolant fluid is actually a mixture of water, yeah, approximately 60%, which is relevant for the actual heat transfer. And then there is added alcohol for protection against frost, approximately 38%. And in addition to that, several additives for protection against corrosion. So this is the actual mixture: water, alcohol, and some additives. Okay. What is also very, very important is to guide the coolant in the right way through the crankcase and the cylinder head. And for this, actually the same rule as just mentioned for the radiators applies, means the coolant first needs to pass by cooler parts of the engine before it reaches the hot regions. Yeah, in order to not heat the one with the other, this should then be the right sequence to apply. But there are, meanwhile, especially for motorbikes, also combined air and liquid cooling systems established. So, for example, the latest BMW GS motorbike has such a system applied. So, as you maybe know, approximately 80% of the heat is created in the region of the cylinder head. So this is where the combustion takes place. This is where the heat is actually generated, and this is also the region where the heat can cause the most damage, right? So yeah, as mentioned, one of the major issues with insufficient cooling is the uncontrolled self-ignition. And this one occurs in the region of the cylinder head, and therefore the cylinder head must be cooled. Must be cooled very sufficient. And for the crankcase, it's maybe different. So for the crankcase, that does not occur too much heat, and on the other hand, it does also not cause too much damage. And this is why for this engine, one could apply a combined air and liquid cooling. So the cylinder head is liquid cooled, and the crankcase is air cooled, which works very well for a boxer motorbike. As shown on the slide number, let me quickly jump to it. For example, here, as shown on slide number 74, especially for boxer engine, for motorbike, the air cooling might be really sufficient because the airflow directly covers the engine block and can therefore transmit a lot of heat. Okay. Yeah, how to control coolant circuits. There are again several options. So first one, you can change the layout or the flow rate. So as mentioned before, when the engine is still cold, you must not send the coolant to the radiator, but you can go for the bypass. You can go for a shortcut and directly send the coolant again to the coolant pump. And later on, you open the valve and send coolant to the radiator. This is meant by changing the layout of the coolant circuit. Then, when the coolant pump is flexible, when it can be controlled, you can also impact the flow rate of the coolant. And last not least, for sure, you can also control the temperature of the coolant circuit by applying an additional heater to heat up the coolant very quick, or a chiller, which is a heat exchanger between the coolant circuit and the AC system, and which helps to lower the temperature of the coolant for the battery. Now let's quickly check how the thermostat, which I just mentioned, actually operates, how it works. Does anybody of you know about it? Has anybody of you ever heard of a thermostat and how it works? Are you still there?
Yes.
Yeah.
Okay.
Yes.
Did you ever heard about a thermostat?
Yes.
Mhm.
I have.
Yes.
And how does
Yes.
it work?
I think it's like a valve. It controls the flow of a liquid. So when the engine is powered hot, it releases the coolant to go around. When it's a bit cooler, it shuts down the flow of the coolant.
Okay, and how does it work? So how does this valve work?
Is activated by a form of sensors. I can't remember what they're called. What specific ones they're called.
No, it's the metal that's increased with the temperature. The temperature influences the metal, and they open and close with the temperature.
Okay, so actually not the metal is influenced, but a wax inside a piston. So this is shown here. So we have actually a spring, which forces the valve in a certain position, shown here on the left picture, and this position leads to a coolant flow from the engine back to the engine again. So as long as the engine is cold, the coolant does not pass by the radiator, but comes from the engine and flows back to the engine again. And then you have a piston which is filled with a wax, and this wax increases its volume when it's heated up, and then applies a force against the force of the spring, and pushes the valve, as you can see on the right side, in another direction, and finally closes the shortcut back to the engine. And then the coolant takes its way, not directly back to the engine, but to the radiator to be cooled down and to then pass by or flow back to the engine. And the temperature where this happens, where the wax pushes the valve in the other direction, in the other position, is defined by the design of the thermostat. So you cannot actually influence it during operation. It's a passive system. And in order to overcome this, there have been map control VEX thermostats introduced. So actually it's the very same. It's the very same approach, but you can even heat the VEX and therefore forces the thermostat to open much earlier, much quicker. And how would you now make use of such map control VEX thermostat? So why do you think this offers opportunities to be able to steer the opening of the thermostat? Which opportunities does this offer?
Is it to divert pull energy to the engine and stop warmer coolant from going into the engine? So it would allow the channels to be a little bit more simplified.
Some more opinions, maybe.
Suppose when a car is standing, so if it's hot and we need to cool it down, we can use this.
Anything else?
It can use the power that you need to cool it down before. I mean, I forgot the word now, but to see what's going to happen with the engine in the future as you need power.
Okay. So actually, it's like that. So when running the engine with high efficiency and also little emissions of air pollutants, you aim for a very high temperature of the engine, of the coolant, let's say 110, maybe 115 degrees Celsius. If you now design the passive VEX element to exactly this temperature, you might face issues in terms of uncontrolled self-ignition, in terms of overheating, when the driver then suddenly is asking for a high power. So let's consider you are driving steady state operation, maybe 110, 120 kilometers per hour on the highway. Then you could easily go to a very high temperature of the coolant to, again, achieve high efficiency of the engine. But if the driver then suddenly pushes the pedal to accelerate, then the engine may overheat very quick. But if you have a so-called map-controlled VEX thermostat in place, you can achieve by heating, in addition, the VEX piston, a very quick opening of the thermostat, and you can then decrease the coolant temperatures very, very quick, much quicker than with a passive thermostat, which again helps to ensure the protection of the engine. So this is the main advantage of such thermostat, that you can run on high temperatures during normal operations and anyway be able to cool down the VEX thermostat by an electrical actuator, which can be even more quick, which can open the valve even more quick, and also in both directions, which can open and close the coolant flow very, very quick. And the result can be seen here. Yeah, you can see the NEDC driving cycle, which was already introduced, and then you can see the comparison between an engine. It's an Audi 1.8 TFSI gasoline engine of generation 3 with the predecessor generation 2. And the generation 3 already has an electrical actuator to steer the coolant flow, and the generation 2 has not. And the result is that the warm up, as you can see, of the red curve is much, much quicker. Yeah? And then you can also remain here on a higher temperature level, more than 100 degrees Celsius, because you are always able to reduce the coolant temperature very quick by just opening the valve again. And then you can go for a lower temperature when there is an additional power demand, when the driver wants to accelerate from on short notice, let's say. You can decrease the coolant temperature of the engine very, very quick. And if the driver then goes back to normal operation, you can again adjust the coolant temperature very quick. So it can always run on the optimum coolant temperature, let's say, which cannot be achieved by a simple thermostat. Another advantage of such modules when equipped with two valves is that you can apply a so-called split cooling. Yeah, you can have two independent valves to steer the coolant flow through the cylinder head and the crankcase independently. As just mentioned, yeah, the cylinder head produces much more waste heat than the crankcase, and it's also much more sensitive for higher temperature than the crankcase, and therefore it really makes sense to steer the coolant flow through both parts of the engine independently. Yeah, to send the cold coolant to the cylinder head to ensure sufficient cooling there, and to send a lower portion, a lower mass flow of the coolant through the crankcase, where it's not that sensitive for the coolant. Okay. Yeah, I think now it's time to have a little break. Let's continue in 13 minutes. Then I will be back, and until then I will mute myself, okay?
So 30 minutes, right?
1-3. I can also type it here.
Okay.
So 13 minutes, okay?
All right, sir.
Then see you later. Can you hear me again?
Yes, we can.
Okay, great. Then let's continue. Let's talk about the coolant pump. So if you consider a mechanical pump, which is fixed to the speed of the engine, for which operating point would you design such a coolant pump? So for which, let's say worst case scenario, do you need to design the coolant flow of such a pump? So let's consider the worst case scenario. What is the worst case scenario for the coolant flow?
Is it possibly that it won't cool down after it absorbs all the heat?
Yeah, the worst case scenario would be running on a very little speed, in the highest gear, let's say, but anyway delivering a very big power and therefore creating a very high amount of waste heat. So just imagine you're running on a very little speed with a very high load, riding uphill, let's say, in the highest gear, and therefore creating a lot of waste heat. But anyway, the speed of the engine and the coolant pump is very little. So this is the operating point for which you need to design such a pump. And this leads to the fact that when running on high speed in a little gear, the mass flow of the coolant is very, very big. Yeah, you spend too much power on the propulsion of the coolant pump, and you don't even need such a high coolant flow then. And this one can be overcome by using an electrical coolant pump, which can be switched off and on again whenever you need. So you can see in this graph here, the red one representing the mechanical coolant pump, which is directly linked to the engine speed, means you always pump a lot of coolant through the engine, even if you don't need it. And on the other hand, you can see the green graph showing the mechanical or showing the power of an electrical coolant pump. And in the beginning of the load cycle, when there is even no cooling required, you can completely switch off. And only if you need a coolant flow to cool down the engine, you switch it on again. And in comparison to that, as I said, the mechanical coolant pump always runs with a direct link to the engine speed. And this leads to two facts. So first of all, the mean power of the mechanical coolant pump is comparatively high, so more than 30 watts in this case. And the mechanical power of the electrical coolant pump is way lower, not even 5 watts. And on the other hand, again, you cool down the engine more than it's actually supposed. So this is the advantage of electrical coolant pump. But this one can be also achieved to some extent by having a switchable mechanical coolant pump. So you can see, as long as the engine still needs to warm up, the switchable mechanical coolant pump is also shut down completely, and only if you need it, it is switched on. And how to achieve such a advantage, shown on the next slide, by a switchable mechanical pump using a friction wheel. So as long as the coolant temperature is still low, the water pump, the coolant pump, is not running at all, and only if you need it, you apply an axial movement to a so-called friction wheel, which is a pulley between the pulley of the water pump and the belt drive. If you then move the pulley, the friction wheel, in between the pulley of the water pump and the belt, it's switched on, and the coolant pump applies a flow to ensure the required cooling. So in the warm-up phase, which is representing here in the beginning section, there is no movement at all, and later on, as I said, you switch on again. Another option is to adjust the geometry of the coolant pump according to the needs, and therefore you again use a wax element, which is in the lower position, as long as the coolant is still cold, and you don't need the flow. And when it gets warm, it is expanding and changing, as you can see here on the picture, the geometry of the coolant pump, and therefore applies then the required mass flow, which is needed to achieve the required flow. Okay. Yeah, now let's go to slide 123, and we will move on to turbocharged engine, and we will add another energy flow to our Sankey diagram, and it's the energy flow of the charge air cooling. So you can see here, we add another portion on the top for the charge air, but this is not the only thing that changes. Also the heat dissipated by the coolant circuit changes. Yeah, so the cooling of the turbocharger also adds additional heat to the coolant circuit, and the portion of the engine oil increases as the lubrication of the turbocharger, and therefore also the heat transferred to the engine oil circuit becomes bigger. Now again, a question to you. So how does a turbocharger actually works, and what is the purpose of the turbocharger?
A turbocharger is meant to increase the volumetric efficiency of the engine. So it means that you can apply less power to an engine, then it takes the exhaust gas, rotates the turbine, which also supplies more air to the combustor chamber, by increasing the power of the engine.
Okay. And which components do you need to apply turbocharging? So can be seen here on the diagram on the right. So which components does the turbocharger consist of?
A turbine and a compressor.
Okay, and what else? What else do you need in order to control the turbocharger?
You might need a belt. A belt to
A belt?
connect it to the engine. Okay, sorry, no belt. That's for supercharger.
Wastegate.
And what is the wastegate used for?
It allows in the exhaust, the heat from the exhaust to come into the turbocharger.
To bypass the turbine.
And when do you need to bypass the turbine?
When you don't need the load, when you don't have load.
Exactly. So the turbine is designed, to apply the right pressure drop, to apply the right power to the shaft, to power the compressor at little speeds. At little RPM, the turbine already needs to deliver the right power, which means that at high speeds, at high exhaust gas mass flow, the pressure used by the turbine might be too big. And therefore, you use the wastegate to bypass the turbine in such conditions. And when the turbine is used, it further expands the exhaust gas mass flow. As you know, it still has a lot of pressure after leaving the combustion chamber, and this pressure is used to make the turbine run, and the turbine then makes a shaft run, and the shaft again makes the compressor run, and the compressor sucks the ambient air and puts it compress it to a high pressure in order to get more mass, more oxygen inside the combustion chamber. And as the compression goes also with a temperature increase between the compressor and the combustion chamber, there's most likely a so-called charge air cooler installed, which lowers the temperature again in order to further increase the mass density of the charge air, and then you can inject more fuel. You can burn more fuel in the combustion chamber, and you therefore increase the specific power of the engine. And a question to you now is, how does this influence the coolant circuits of the engine? So how does a turbocharger influences the coolant circuits of an engine?
I believe that you need more coolant because of the increased heat from the turbocharger. So you need to have a bigger sump for the coolant to cover the increased temperature from the turbocharger.
Okay, yeah, that's right. So on the one hand, the turbocharger itself, especially the turbocharger of gasoline engines, might be cooled by a coolant. So therefore, you put more heat into the coolant itself. But if the power of the combustion itself is increased, for sure you also create more waste heat in the cylinder head, and therefore the coolant must be more powerful with this respect as well. On the other hand, you also use the engine oil to take care of the lubrication of the shaft between the turbine and the compressor, and not only the lubrication, but also the engine oil takes care of a certain amount of cooling of the turbocharger. And then most likely nowadays the charge air cooler, the charge air is also cooled by a liquid, by the so-called LT liquid, by the low temperature liquid. Okay, very good. Okay, yeah, here you can see now two different variants. So first one, the direct charge air cooling, which uses a separate radiator in front of the vehicle on the left side, and the indirect charge air cooling, which uses a liquid to cool down the charge air. And what might be the advantage of the indirect charge air cooling in comparison with the direct charge air cooling?
More heat can be removed from the charge.
Yeah, this is one aspect, and another one. What might be another one? Another advantage is that if you transfer the heat to a coolant, then this might again help to warm up the whole engine. So if you transfer the heat of the compression directly to the environment, it's lost. But if you take the heat and transfer to a liquid circuit, then this might help to heat up the engine again. Okay, very good. Yeah, let's now talk about the water injection. Does anybody of you ever heard about the water injection and the purpose of the water injection? What does the water injection help for?
Engine temperature.
Can you maybe better explain?
Is it to lower the temperature of the cylinder?
Oh my god.
So what happens if you inject water in the combustion engine?
You mean directly into the engine?
Exactly, yeah.
Water compression ratio is higher than that of gasoline. I think it will damage it.
Yeah, it depends on the amount of water, yeah, maybe. But what happens if you inject the right amount of water, the right quantity of water in the combustion chamber?
It will decrease the temperature inside the chamber.
Exactly, yeah, because the evaporation helps to reduce the temperature there. And which advantage does such a cool down of the inner temperatures of the combustion chamber provide?
The durability of the engine.
Yeah, as mentioned several times, one major issue of the combustion is the so-called self-ignition. So we already know that when increasing the compression ratio, the uncontrolled self-ignition may occur, but only at very, very high loads. Means when running on low loads, on part load, let's say, you could actually go for a higher compression ratio to further support the efficiency of the engine. And this does not cause any issues when running on part load. But as the compression ratio is considered as fixed, given by the design of the engine, this may occur to issues when running on high load. This is exactly the case when the water injection can utilize its advantages. Means you can design an engine with a very high compression ratio to be very efficient in the part load. And when then running on high load, you can utilize the water injection to further cool down the combustion chamber in order to avoid any damage to the engine. So this means you can achieve a better consumption for the part load, and you, on the other hand, you don't face any issues when running on high load, because then you can apply the water injection and avoid any damages. And this also helps to further cool down the exhaust gas, and you don't need to decrease the fuel mixture ratio in order to cool the turbocharger and also the exhaust gas system by unburned fuel. So both things help to decrease the fuel consumption of the vehicle. But on the other hand, you need to add another system to the vehicle. You need to add a tank for the water. You need to have a water pump. You need to have a filter. You maybe also need to have a high pressure water pump to inject the water via special valves to the combustion chamber. And then we have again a trade-off. You need to consider whether this this one is valid to apply for certain vehicles. So this one does definitely not make sense to low-cost gasoline engines or something, but might help to further increase the efficiency and the robustness of state-of-the-art gasoline engines. Okay. As you can see, we have now step by step developed our energy flow diagram, starting with the idealized Otto engine, going over to the two-stroke engine, the four-stroke engine, naturally aspirated engine, turbocharged engine, including the water injection. And now in the last step, we will then consider a hybrid engine, and we need to add another coolant circuit to our diagram because the high voltage battery of such vehicles might not withstand temperatures above 30, 35, maybe 40 degrees Celsius. And therefore we can no more apply a normal coolant circuit, but we need to use a refrigeration circuit to be able to cool down the battery to temperatures below the ambient temperatures. So therefore, again, we need to add another circuit, and it become a more and more complicated energy flow diagram. As you may have already recognized, the thermal management of state-of-the-art powertrains is more and more complicated. More and more coolant circuits applied, but anyway, the efficiency goes up. And how can you explain this? So on the one hand, the efficiency goes up, but on the other hand, the requirements to the coolant become also higher. So actually, this looked like contradiction, but how can you explain it? So as I said, the waste heat transferred to the coolant circuits become more and more, but at the same time, the efficiency increases. So how can this be?
Why don't more cars have water injection?
Is it because there's less heat dissipated and lost, not recycled, basically?
No, this is not the answer. Any other opinions?
I need a poop.
So the reason for this is that especially when applying a turbocharger, we take more and more heat from the exhaust gas and transfer it to closed coolant circuits. And therefore, the closed coolant circuits needs to be more powerful, even so the efficiency of the engine, of the powertrain went up. So this is the reason behind when having a very simple engine, a naturally aspirated engine, maybe even an air-cooled engine. For sure, you don't transfer too much heat to closed circuits, but with latest engine, turbocharged engines, it's actually the opposite. You take more and more heat from the open exhaust gas circuit and transfer it to a closed circuit, which then leads to higher requirements for such closed coolant circuits. And yeah, to conclude this chapter, I would like to again check a more sophisticated Sankey diagram as shown on slide 139. As you know, we've tried to figure out how these different energy flows can be actually explained. But if you do a more detailed analysis, you will recognize that the distribution of the energy flows can be even more detailed. You can check all the different heat flows, not only for the coolant itself, but also for the cylinder head, for the crankshaft housing separately, and then this will lead to a way more difficult Sankey diagram. But I think for the scope of our lecture, the approach we've just applied is definitely sufficient. And the main idea is that you know how all the different energy flows are actually created, starting with the idealized Otto engine. Okay, so far for the thermal engines, and then we will move on to the e-motors. And first of all, we will start with the general architecture of electric powertrain. So maybe somebody of you can quickly explain which components are needed for an electrical powertrain. So what are the main components for such powertrains? What do you need for an electrical powertrain?
Battery pack and motor.
So how does the whole story begins? So let's start with the charging. So which components, do you need for electrical powertrain? Charging, battery, and so on and so on. So which components do you need? Yeah, this one is shown on slide 142. So first of all, you need a charging socket, right? This is where you plug in the cable, where you start the charging. If you do AC charging, so if you use the electricity which is available in your home, then this one is AC electricity. Then you need a so-called onboard charger, which transforms the AC into DC to then charge the battery. So this is the first step: plug in the cable, charge the battery via the so-called onboard charger. And then during operations, when the vehicle is running, you again need a power electronics, a so-called inverter, to transform the DC electricity into AC, most likely into a three-phase AC current again, to make the e-motor run. On the other hand, you will still have a 12-volt electrical net on board to make all the low power consumers run, such as the HiFi system and so on and so on. And this is why you need a DC-DC converter, which transforms the high voltage electricity of the battery into a 12-volt electricity to make all the auxiliaries, as mentioned, run. And all these components of the electric powertrain, for sure, they also require a thermal management. They also need to be cooled, as during operations they have some losses, and therefore the temperatures may rise above the allowed limits, which are mentioned here on this slide. So for the power electronics, you use different electronic devices. You use resistors, capacitors, diodes, transistors, integrated circuits, for logic operations, and all of them have upper temperature limits of or between 105 and 150 degrees Celsius, and in order to not exceed them, you need to cool these components. Yeah, let's now talk about the losses of an e-motor. Most important are the so-called copper or ohmic losses. So I think you still know from other lectures that the dissipated power is equal to the resistance multiplied with I square. And the ohmic resistance, by the way, is not only depending of the material, but also of the temperature. And this is a self amplifying effect. The hotter a conductor gets, the higher the ohmic resistance also becomes, and therefore the dissipated power becomes more and more, and this is why you need to ensure the right cooling of an e-motor. Another negative effect, another contributor to the losses of an e-motor is the so-called hysteresis loss. So when applying an electromagnetic field to the ferromagnetic material of the e-motor, of the stator or the rotor, there are always losses occurring, which again create heat, which then needs to be cooled away, and the occurrence of this ferromagnetic losses is especially high when you use massive material, because then a lot of eddy currents can occur, and this is why the stator as well as the rotor of e-motors are not made out of massive material, but there are individual sheets with insulation in between are used to avoid the occurrence of eddy losses, of eddy currents, by isolating the different sheets from each other. So if you use thin metal sheets, there cannot occur too high currents in comparison with the massive material. Okay. Then there are also mechanical losses to consider. First of all, flow losses. For example, do you have a question? No. So please let me know if there's a question, okay? And anytime ask. Mechanical losses occur, for example, as flow losses. For example, in the air gap between stator and rotor. Then for sure you have frictional moments in the bearing of the rotor. For DC excited motors, there might be also some mechanical losses for the sliding contacts. And last not least, shown here on the right, there are also mechanical losses to consider in the gearbox of the motor. And all these different components of the motor has got the same with the power electronics, upper temperature limits to not exceed, and this one must be considered for the cooling. So for example, the windings of the e-motors, which are highly affected by the copper or the ohmic losses, might not exceed temperatures of 180 degrees Celsius. The permanent magnets might not exceed temperatures of 140 degrees Celsius, because otherwise they will face irreversible demagnetization. The bearings might not exceed 60 degrees Celsius, and the gearbox oil might not exceed 70 degrees Celsius in order to ensure a sufficient lubrication. Okay, here you can now see a highly integrated system, means e-motor, which is completely, including all the auxiliaries, integrated in one central housing, which also covers the inverter, the component to transform the DC current of the battery into the required three-phase AC current for the e-motor itself. Also the control unit is included. Then we've got the gearbox, including differential, also parking lock included in order to fix the gears when parking the vehicle. And there is an oil module, including heat exchanger, which transfers the heat of the oil to the coolant circuit as well included. Then you need to cool the housing and also the stator of the e-motor with a coolant. So even so, the efficiency of the e-motor is comparatively high. Maybe 80, maybe 90 you anyway need to cool down the remaining waste heat, and this also applies to the inverter, and as mentioned, to the heat exchanger, which transfers the heat of the gearbox oil to the coolant circuit. Okay. Any questions so far? Can you still hear me?
Yes, I've no
Yes, yes. No questions.
Okay. No questions. Okay. Great. Yeah. Then let's talk about the battery of an electrical powertrain. But first of all, before moving on with the lecture notes, do you know of which components a state-of-the-art high voltage battery consists of? Do you know what's inside such a battery?
I think lithium.
Yeah, this is for the battery cells, but when talking about the architecture of a high voltage battery, which components do you need to mention?
A battery management system.
Okay. What else?
And for higher demand, higher loads, maybe some cooling for the battery pack.
Okay. What else?
A kill switch, just in case you want to shut off all the power.
Exactly, switch. What else? What else is missing?
Temperature sensors for the temperature of battery.
Exactly, yeah. Yeah, so thank you very much. You already mentioned many very important things. So the inside of a battery is very, very complex. So first of all, you have got the cell modules, which store the actual energy, but you also need to manage the cell modules, and therefore you need to measure several parameters. You need to measure the cell voltage, and you also need to measure the temperature inside the battery. So when the voltage differs too much, there is a so-called cell balancing applied. Means you have ohmic resistances, which can decrease the voltage of the cell to the required level. Then you also, for sure need to know about the temperature of the cells in order to decrease the power to not overstress the cells. And this one is managed by the so-called battery management system. But the battery management system does also do more. For example, it also manages the main relays of the battery. So you need to be anytime able to switch on and switch off the battery. So for example, if the vehicle is standing still, if it's turned off, you just switch off the battery, and the same applies in case of a crash or something. then you need to be able to immediately switch off the battery due to safety regulations. And last not least, for sure, also the cooling of the battery must be considered. You must even apply a very sophisticated cooling as the upper temperature limit of the battery is actually very, very low. So the operational area of a lithium-ion battery is between 5 and 40 degrees Celsius. So this is a very narrow area, as you can imagine, because combustion engine can operate from minus 20, minus 30 degrees Celsius up to more than 100 degrees Celsius. So in comparison, the operational area of the battery is very low. And if you go below the 5 degrees Celsius, you might have a risk regarding the reliability, and therefore the battery must be heated. When the temperature exceeds 40 degree, maybe 50 degree Celsius, you've got an issue with the endurance, and therefore you need to apply a cooling to the battery. Additional measures might be a load reduction. So if the temperature rises too fast, to too high levels, then you might, as I said, reduce the load. And if you then reach temperatures of 100 degrees Celsius or more, you might even have an issue with the safety of the battery. So therefore, the cooling is very, very important. And as the allowed temperature might be below the ambient temperature, you need to apply a AC system in order to cool the battery. And therefore, there are different approaches in use, as shown here. On the slide, yes. For example, you can blow cooled air to the battery. So means first you use the AC system to cool down the air, and then you use the cooled down air to cool further on the battery. Or you might even design a own evaporator inside the battery. So as explained yesterday, then the liquid refrigerant flows into the battery, evaporates there, and ensures the required amount of cooling. Another approach is shown on the very right diagram is to cool the battery with a liquid. But in case the temperature of the liquid is too high, then you can further cool the liquid with the AC system by using a so-called chiller. So the so-called chiller transfers the heat of the coolant to the AC system, and then you can again achieve the required temperature. Okay. So far, so good. So I think we should now go for a break for 30 minutes, and then continue with the hybrids, the brakes, and last not least, the recovery. So yeah, I will be back in 20 minutes and mute myself until then.
is 18, 19 meters. Beautiful, beautiful deck up here. Really cool chill out space here. Everything carbon, huh? Everything carbon for lightweight. Sunbeds here. Check out the amount of ropes for the sail. Of course, you know, sailing with wind power. Obviously, that was stupid to say that, but anyways. All right, let me take you through what makes this boat eco then. So first of all, of course, a lot of solar. So you can see the whole roof full of solar panels. To charge the batteries that are the energy storage of the boat, and then also teak being made from recycled teak, so that's really cool as well. So we have this really cool Italian material, it's called Phoenix. 60% is recycled paper, then some resin. It has this kind of memory ability, so if you scratch it, you warm it up, it like comes back to being in great shape. So impressive new material there from Italy. And now we're gonna go check out the batteries quickly. Okay, so we're really having some difficulties here with the lighting. Huh? Alex is on me. He's like, no. For indoor, you need to do this. Outdoor, you need to do this. So what do I have to do for now for a setting?
If you're outdoor, you gotta close the
Okay, so now I'm outdoor. Am I good?
If you're outdoor, you're good.
I'm good.
Conditions should be
I'm good.
fine.
Alex says I'm good. So have a look now. Wow, that's a cool system.
Yeah.
That's an epic.
No
that's
handles.
an epic system. No handle magnetic hatch remover. How cool is that? Okay, so we're loaded up with batteries, and you can drive 8 hours, huh? 8 hours with one charge. So that's quite a distance. Very, very cool. And the solar, of course, solar helps to keep more charge along the way. And nights also not a problem. Just on one full charge you can do 50 nights of aircon, because you use only up to 10 kilowatts for aircon per night, and you got 160 kilowatts in those batteries there. You think catamaran there's not going to be much space because you're in that thin hull, but actually look how much. I mean, it's really epic how they managed to maximize the space. Huh? The bed obviously goes, you know, it's like this is the end of the hull, so it uses the space of going up into it like that, and the hull actually stops there. So we're just leaving the harbor now, and that's the beauty of electric powered boats. I mean, look, it's just almost totally silent. You can hear nothing. A little bit of a zooming here because I'm right where the engines are, but out there is totally silent. So that's really, really beautiful, and that's what I love. And then, so it's like being with a sail, huh, when you're electric powered. Interesting point that you made about the whole electric motor being a very, very new innovation.
Comparing to the automotive industry, we like a Porsche Taycan because we are using 700 volts now. In the previous system we used 350 volts like a Tesla, so now we are on the highest possible voltage, which is more efficient, and we are more lighter.
Good, thank you very much. So, and now we have the honor of having Francis here. Francis is owner and founder of Sunreef, and we're going to have a small chat.
Yes, hello.
Du wolltest noch mal ein bisschen hier vom Steuerbord noch ein bisschen was erklären.
Hier sieht man eigentlich unseren Startbildschirm. Das meiste ist möglichst einfach gehalten. Es ist ein bisschen viel Technik hinten dran, aber wir haben versucht, so ein bisschen Apple und Tesla zu kopieren. Natürlich, wir heute alle können hier gleich auf den Generator gehen, können wir gleich mal einen starten. Dann sieht man jetzt, wie der läuft.
Mega leise, ne?
Der Eigner hat extrem viel Wert darauf gelegt, dass das Generator sehr leise ist. So, jetzt Medium. Dann gehen wir jetzt hier hoch auf 40 Kilowatt oder wir können auf High gehen. Im Moment haben wir das gesetzt auf 60. Wir könnten noch mehr, aber wir wollen nicht ans Limit gehen.
Toll, wie einfach ihr das dann dargestellt habt, ne? Also
relativ,
ja, relativ, dass es user-friendly ist. Und
ja, es sind drei Computer hinten dran. Also jede Seite vom Schiff hat eigentlich seinen eigenen Computer. Und wenn eine Seite abstellt, dann können wir umschalten und die linke Seite vom Schiff übernimmt die rechte Seite. Also viele Backups auch dabei.
Wo ist der Stuhl?
Oben.
Und hier stehen?
Na, hier.
Wenn es regnet, die ganze Nacht durchstehen, oder was?
Das ist ein Segelboot, das stellt man vor außen.
Immer draußen?
Ja.
Bei Wind und Wetter?
Ja, Wind und Wetter, Segelboot ist draußen, ja.
The most awesome spot right in front here. So subscribe to this video please, because soon I'm going to be launching the video of my catamaran once it arrives, and we're going to do a boat tour on that one. It's still a bit different to this one, so I think you'll quite enjoy the tour. So subscribe so you don't miss out when I launch that video. so that's it for the day here. We're just back in the harbor now. And now somehow I'm gonna magically try and get off this boat. Oh, yeah. Thank you very much. So Francis is leaving to the next meeting, trying to sell some more boats. But what an epic boat really. It's lovely, and so much space on that boat. Great how they're living the whole theme of sustainability. That's awesome. So I hope you enjoyed it, and subscribe now, because my boat is going to be coming live soon. We can call it the Crib Tour. So subscribe so you don't miss out on that video, please. Thank you for watching. Bye bye. Welcome everybody to Poland. So luxury yachting, even in the face of climate change, luxury yachting is it's not going to go away, you know. So what you have to do is you have to offer people solutions which allow them to keep going with luxury yachting, but just in a much more sustainable manner. And this is what brings me today to Sunreef here. You've all seen the little boat tour that I did with you about a teaser in Monaco, and this is the boat that's being built here. So we're going to take you around the whole production. Francis is going to explain everything, so come along. Hello Francis.
Hello Nico.
We meet again. I just told everybody that they've all seen the video from Monaco. So we meet again here. Thank you. Now in your production facility, and it's a new production facility.
Yes,
what is
totally
your plans?
In the center of the city of Nantes, we have the old facility, and now we moved to the new facility. We have a lot of new contracts for the Ecoline. We need more place for produce these old boats.
And I've heard it's very tough for your employees, because you could do everything better than everybody else because you're an engineer yourself. So you're very, very demanding. Yes. Let's go inside and we check out the expertise. Francis, once the design is ready, you have to go into the build. And here we're at the first part of the build. And this is all about the negative molds, no? But tell us a little bit more.
This is the CNC machine, one of the biggest in Europe. Here we build all the negative, sometimes also the positive mold, to make the holes on all pieces of the boat, what we make in composite or in different materials.
And when it comes to more sustainable composites, what is your plan with that for the next couple of years?
We are going for the basalt. We are making some tests. We must agree this all by the norm, road norms. I think in the next 2 years we can build bigger boats in basalt and different materials.
So starting from next year, the hull for smaller boats is going to start to be basalt and linen.
Yes, we have a plan for next year, build a 40 feet boat in basalt.